So, good afternoon, everyone. My name is Gert. I'm from Belgium, from Hasselt University. I'm a researcher in business engineering, and today I want to talk a little bit about how using Bayesian Inference and MCMC to enhance discovered process models. So I'm not a statistician or a Bayesian statistician, so I'm not going really in depth in the technical part. I'm trying to focus more on the business part. I'm working together on this with colleagues from the Faculty of Statistics at our university. So if there are any Bayesian experts in the room who might have some useful comments or suggestions, I'm really glad to hear those. And if there are questions, I try to answer those too. I'm going to start with a little question, and it's who of you has already heard about the term process mining? So a few hands in the room have. Process mining is basically a sort of process-oriented data science. The problem is that it has developed quite isolated from the real data science community, let's say, the people here, or you know what I mean, because it's originating from the business process management field. But in the recent years, there are much more efforts to close that gap. But I'm going to really quickly explain what process mining is about. So we start with a process that happens somewhere, typically in a company. That can be very boring sounding processes, like from order to cash or procurement to pay. But the type of processes is really wide. So you have customer journeys, coming back to a store, getting emails. How does the emails have an impact on their journey and so on? How do we learn? So educational trajectories. What are the procedures in a hospital? How can we sort of manage the emergency department workload and so on? So there are many different processes, many different contexts. What all these processes have in common typically is that there is data that is generated, which we call an event log, so a logbook of events, which always have these three different characteristics, which is there are activities, events, tasks which happen for a specific case. For instance, a specific invoice, and it is paid, it is written off, and so on, at a specific point in time. So we have these three things: activity, case, and timestamp. And what we then try to do is, from this data, this event data, we try to discover process models, these flowchart kind of things. For this discovery, there are lots of algorithms. Some work well on some data, and others work well on other data. I'm not going into detail about that. There are also different notation for process models. Today I'll be using the business process model and notation, which is one of the standards and one of the most easy to understand. We basically have two circles, which are the start and the end points of a process. We have these rounded rectangles, which are the tasks in a process. And we have these diamonds of different types, which are splits and joins. You have this cross diamond, which is an exclusive OR, so you have either take one part or the other. And then you have these plus diamonds, which is an AND split or join, which means that you're going to take multiple parts together simultaneously. So let's show you an example. If you go to user, some of you might have to start with request funding from your superiors to go to user. This funding can be granted or it can be rejected. So there's a choice here that probably your supervisor has to make. And based on that, we can decide whether to go or not. So we can cancel our plans and cry a little bit. Or we can go and then we start registering for the conference, booking our hotel or train or a flight maybe. And these last three activities are activities that don't have a fixed order. You can choose in what order you do them. And that's one example of a process, and this is one process that could be discovered if we had, for instance, this data, how this process went for all of us here today. But these type of process models we find have a huge disadvantage, and that is that they don't discover or they don't learn probabilities. So we see more or less what takes place, but now not how often or how different choices are related to each other. For instance, if my funding is rejected, the probability that I'll have to cancel my plans will be a little bit higher. It probably more makes sense to first register and then book the train, because otherwise maybe the conference is sold out and I have wasted money on my train tickets and so on, even though there is no fixed order. And that's basically what I'm trying to do with Bayesian Inference and MCMC, is to learn these probabilities and dependencies between different elements in the process. So I'm going to take another example, more abstract example, where I have 6 activities, A, B, C, D, E, F. And among these 6 activities, I have a process which has recorded 4 different process executions, 4 different sequences of these activities. And from these sequences, I can discover a model. And in this case, it's very simple because all sequences start with A, they end with either E or F. The last but one activity is D and so on. So it's basically 2 choices in my model. If I want to add probabilities on that, I can just define them. So I have a zeta1 and a 1 minus zeta1 for the first choice, and I do it with zeta2 and 1 minus zeta2 for the second choice. What I do then is I start to create a Bayesian model. This model here looks a bit like R code. It's OpenBugs or RinBugs Bayesian modeling. So I say that my data is actually the result of a multinomial distribution with 4 different probabilities and a certain number of observations. These 4 different probabilities, one for each sequence, is a combination of the zeta1 and the zeta2 I defined. And I can set priors for these 2, zeta1 and zeta2. So for instance, I might have an idea as a domain expert on what these probabilities, a sort of prior belief about these choices. In this case, I'm using a beta distribution with shape parameters 2 and 2, which means I think that it will not be like the extreme 0 or 1 probability, but somewhere in the middle. But you can change this depending on the process. And then I have my data, which are the trace frequencies and the number of observations. And when you then use MCMC, you can get these posterior probability distributions, and you see that the second choice is much more unbalanced than the first choice in this example, which means that in the second choice we were much more probable to take one path over the other, while in the first choice is zeta1, it was closer to 0.5, which means that both choices were more or less equally probable. And that's very useful information in a process analysis context. But that's not the end, of course, because if you look at the frequencies we have here on top, we see that there's probably more going on. There's probably a dependency between choice 1 and choice 2. And depending on if I execute B or C, I might be more or less probable to choose E over F or not. So what I can do is, instead of talking about zeta2 and 1 minus zeta2, I have actually 2 probabilities, and one of them will be sort of valid or enabled depending on the choice I've made earlier. So then I can change my 4 trace frequencies, 2 of them now taking into account the new probabilities, because something happened which actually put the case of the process in 2 different worlds, because something else happened, so its probability will be slightly different maybe. And then I can also ask, what's the difference between those 2 worlds, the difference between those 2 probabilities? And when we do the MCMC again, we see that zeta3 is much higher than zeta2. So depending on my first choice, I have an even bigger choice that I choose F over E. And the delta between them is significantly different from 0. So there is a probability dependencies between those 2 choices, which also is very interesting. And now I'm looking very locally at these 2 choices, but using the Bayesian models, we can also get this deviation information criteria, which let us allow, from a Bayesian statistical viewpoint, which of these process models overall is the best fit with our data. We see that the second, where the probabilities were dependent, has a lower DIC, so it's a little bit better in fitting, in explaining the data than the first model. But of course, that's a very simple example, and in real life, processes are very complex, and we will not be able to really, for each trace, sort of put these probabilities together manually. What might happen if we just look at this process, which is not very complex, but already a little bit more complex? We said that these 3 activities can happen in any different order. Well, that's a very different case, very different from just a choice. How do we define probabilities in such a case? And if we go to 4 or 5, then the number of different orderings increases exponentially. Another problem is if we have a loop, if we can ask different institutions for our funding, then we have more different types of traces, and we would have to define probabilities for all the different types. But how far can we go? Because we can have very long traces. In the end, the probability will go to 0, but we don't know that up front. And there also might be observations in the data that don't really fit the model that we discovered. Some sort of outliers, people that registered, then booked their hotels, didn't get funding, had to cancel their plans, and then cry. That's not explained by my model, but it might be in my data. So how do I model that in my Bayesian model? So how to tackle these complexities is why we came up with this R package that's actually going to create a model for you, and you don't have to create it manually. This is a slightly more complex example with 12 different sequences, a specific model. Some sequences do not fit the model, but the model has also sequences which were not in the data, and so on. What we then do is we actually list all the different sequences, and we work back to the beginning of the model by creating a prefix tree. And based on these prefix tree, we can then see where do we have to define probabilities, and by combining them, we get the probabilities of ending up in a specific leaf of the tree. This is only for the data that we saw and that is in the model. There can be additional arcs, which we call in process analysis escaping arcs, which are places in the model where something else is allowed to happen, but we didn't see it. So we can add these to the model to fit with those unobserved types of behavior. And we can go back. Then we can define probabilities for all these splits in the model, and then we can combine them to see what is the probability that B, C, E, D, H, G occurred in our process. So that's a way that we automated this construction of Bayesian modeling. And then we also added a sort of bypass to come up with the fact that some guys who first do the registration and then do the funding might not fit in my model of the process. So there's a sort of probability there also. What is the probability that a process execution is not compliant with my model? And using this automated approach, we get the same type of model, but much more complex, but we don't have to put it manually together, and we can just run it. And what can we do with it? Well, we can see what is the impact of rejected funding on my canceling of my plans. Is there an impact or is there no impact? What is the relationship between register and book the train? Will we first register or book the train, or is it really independent of each other, and so on? But what we also can do, we can test different models and see which one of them, which specifications of these two process models fits best with the data. Because we will never find a model that is perfectly fitting. We have problems with fitness and accuracy, with recall and accuracy, recall and precision in process discovery. So we have trade-offs, and there are a lot of problems in measuring the quality of these models. And this is actually a new approach to have a sort of goodness of fit for these models, which is a totally different view, and it really comes down to connecting these data science statistics field with the business process management field, which have really different views from each other. And all this is available in a package called propro for probabilistic process models. It's not yet on CRAN, it's available on GitHub. And it's actually so what it takes is it takes the process data, it takes the process model, and it gives you a Bayesian model, and then you can see do certain hypotheses hold or not. And actually part of BUPAR, which is a larger set of packages in R for business process analysis. So BUPAR is providing the methods to load your event data, make sure that there's an event log, to load the process models. And what BUPAR actually did until there was propro is really the descriptive and exploratory analysis of these data to actually discover these models based on the event log. And what propro does is actually adding this additional part of a statistical model on top of the process model, making the process model not just a non-stochastic model, but also allowing you to test different hypotheses. And that's actually with our aim to take this process discovery to increase our understanding of business processes to the next level. Thank you.
Thank you. Time for a question? Thank you. Oh, okay, one question.
So, when you're doing this for real, how important do you find the priors to be?
We're not yet sure about that because we're still working on doing it on real cases, because the problems we're having is that the discovery algorithms for process models have so much difficulties with real cases that it is hard to find a good process model. And if you don't have a good process model, doing the statistical building is like garbage in, garbage out. So what we actually need is have very specific use cases where we can zoom in on specific activities so that we don't have large models, and then it's easier. About the priors, we're not yet sure how important that is, because also to validate that you will need companies who have prior knowledge about their processes, and that's typically very hard to find. Also because very often processes are very, let's say, secretive part of the processes, so they're not always very... One problem is that they don't have a clue how their process is running, so they maybe not have a prior knowledge. And the second is that they don't really want the results to be made public very easily. So that's still something we have to look at, the setting of these priors. How can we use the domain knowledge, and how important is it in the actual analysis? Thank you.